Hello everyone, today I will be going over the 2016 final exam for Organic Chemistry 2, and I will be doing the nomenclature and reaction section. And before we get started, I want to say that even though this is the 2016 final exam, some of the questions were relevant to chapter 19 material, so I have taken those out and replaced them with questions from exam 3 or exam 1 that are relevant to what we have covered, since we have not covered chapter 19. And I hope that will make this review as useful as possible to study for the final exam. Okay, so let's get started with nomenclature. And as you can see, all three questions are carboxylic acid derivatives, right? So these are perhaps the hardest type of nomenclature questions that we have encountered in organic chemistry. So what I decided is let's do a mini review before we jump into these questions, just so we can all get familiar with how to name these. And it can be a little bit daunting at first, but hopefully I'll give you some tips, and that will make it a little bit easier when you try to name these. Okay, so as you can see here, we have 5 compounds, and they're pretty similar. The only difference is this highlighted part in yellow, right? So all of these are carboxylic acid. The first compound is a carboxylic acid, butanoic acid, and all of these are derivatives of that butanoic acid. And what I want to show here is how similar it is. So if you can name the carboxylic acid, it'll be very easy to name the derivatives of it, right? So to name the carboxylic acid, what you want to do is count how many carbons are there. So 1, 2, 3, and also count the carbonyl carbon. Okay, that's a common mistake. You don't want to miss that one, since that is also a carbon. So that's 4. Then name it like the alkane chain, so butane, right? And then get rid of the E and add oic acid. So you get butanoic acid. Okay, so that's how to name the carboxylic acid, right? Let's get rid of that. So naming carboxylic acid is easy, right? Then the next compound we have is an anhydride, and this is very similar to the carboxylic acid name. The only difference is this N bit, it says anhydride. Okay, so you name the carboxylic acid. So we have the same thing here, 1, 2, 3, 4. So that's butanoic acid, and then instead of acid you put anhydride. Okay, and there's another example I have of this, because in this example we have both these. You'll notice the alkane chains are the exact same. Okay, so this is called a symmetrical anhydride. So that's why we can just name it butanoic anhydride, because both of them are butanoic acids, right? But sometimes we have that the alkane chains on either side of the oxygen are different, right? So how do we name those? I'll go over in a little bit. Okay, but this is the simplest case where we have just the symmetrical anhydride. So you just name one of them as an acid, and then instead of acid put anhydride. Okay. Then the next one compound we have is an ester, and for esters you have same thing here. So this is the butanoic acid part. That's the same. So you name it butanoic acid, and instead of oic acid, instead of ic acid, you put ATE, 8. Okay, so butanoate, that's the parent chain, and then this extra bit that's attached, instead of like the OH in the carboxylic acid, you have this O and then a R group. In this case, it's methyl. So you just name that R group as you would any R group substituent, right? So in this case, it's a methyl, so you just put methyl butanoate. Okay, and you'll notice that all the parent chains are exactly the same, except you're just changing the ending bit, right? So that's why it's critical that you become very good at naming the carboxylic acid, and naming these will become easier. So let's go to the next one. It's an amide, okay? And how you know it's an amide is it'll have the NH or NHR or NH2 group, right? So just look out for those, and that will give you a clue it's an amide. Okay. So how you name an amide is same thing. Name it as the carboxylic acid. So carboxylic acid is butanoic acid because it has 4 carbons. Okay. And then instead of the oic acid, you put amide. Okay. So it becomes butanamide. Right. And also for this, we have this is an unsubstituted amide, meaning there's only hydrogens attached to the nitrogen, but you can also have R groups attached to the nitrogen. So we'll go over how to name those also in a little bit. Okay, and the last compound we have is a nitrile, and these are not really carboxylic acid derivatives, because you'll notice like it doesn't have this C double bond O, this form like R C double bond O and then whatever group. It doesn't have that form, but it's still included in this chapter, and we need to know how to name them. But the good thing is it's very easy to name. So what you do is you name it. So you name the alkane chain. So you have 1, 2, 3, 4 carbons. So you name butane, and then you add nitrile at the end. Okay. So whatever the alkane chain, you name it, and then you add nitrile at the end. So very easy. And then also one note I would add to this nitrile is sometimes you might see it as a substituent because this is the least priority out of all these. So when you see the nitrile as a substituent, you name it as a cyano. Okay, so keep that in mind. Cyano. So this is the only one out of these that can be named as a sub. Okay, and then so let's go over these extra examples, a little bit harder examples of the amide and anhydride cases. Okay, so the anhydride case I have here is where it's an unsymmetrical anhydride, right? So we have basically we have 2 carboxylic acids, right? So you have this either side of the oxygen, and you have that one, right? So the easy way to do this is just name the carboxylic acids. So this is butanoic acid here, and this is propanoic acid on the right, and then add anhydride. Get rid of the acids and add anhydride, and put them in alphabetical order. So butanoic, B is before P, so that's why you put butanoic before propanoic. So you will name it butanoic, propanoic, anhydride, right? So, and yeah, so keep in mind that it doesn't matter. Like the right side will not have priority over the left side. That's not how it works. It is based on alphabetical order. So if you have 2 different alkane chains on either side of the oxygen, then you need to name both of them. Okay. And then for the amide, we have this example with a substituted amide. So what that means is it's not just an NH2 like we had in the first example. This is an NH with a R group, right? So how do you name these? Well, the parent chain is the same, butanamide, as we discussed before. That's how you name it. So you just count the carbons, and then you do butanoic acid and put amide instead of oic acid, right? And then this extra bit, the substituted part, how you're going to name it is as a substituent. So in this case, it's a methyl group, but usually we put like 2-methyl or something like that, right? But here, we're not going to do that because we do N-methyl because it's attached to the nitrogen, okay, to indicate that it's attached to the nitrogen. So anytime you have a substituted amide and you have some alkane, so you have some R groups attached to it, you need to specify that they are attached to the nitrogen by putting N, whatever the R group is, right? So yeah, so this is basic overview of how to name these carboxylic acid derivatives, and so hopefully you guys are all caught up now, and you can maybe, if you want to take a screenshot here, you can do that. Let me zoom out. There we go. So yeah, so I just chose these examples just to show how similar these are, and so if you recognize the pattern, it'll become easy to name these, right? So they're all parent chains are all butanes. So just show you guys how to recognize the pattern. Okay, so now let's jump into the example. So first example we have is, so first thing you want to do when you look at any nomenclature question is what type of molecule do I have, right? So in this case we have, this is an R group. We have another R group here, and then we have this double bond O and O in the middle, O. So this is, looks like this, COO CRO, right? And this is anhydride. Okay, so recognize, first thing you want to recognize is what am I working with? What type of molecule, right? So in this case we have an anhydride, so I'll put that down, and you might just not put it down, like you might just have it in your head, but I just like to put it down because now I know what rules I'm working with, right? So what are the rules of anhydrides? As we discussed before, you just name the, it's like made up of two carboxylic acids, and you just name those and you add anhydride at the end, right? So seeing this, writing it down, it just notifies me like these are the rules I need to keep in mind when I do this, right? Okay, so let's go ahead and get started. So we can see it's not a symmetrical anhydride, so it's not the easy case. It's a little bit difficult, but not too bad. So what we're going to start doing is numbering these R groups attached to either side of the O. We're going to start numbering it from the carbonyl. So 1, 2, 3, 4, 5, okay? And same thing here, I'll number it with red. 1, 2, 3, 4. You don't go up there because this will give you a 3 carbon chain, but you want the longest chain possible. Okay, so you have a 4 carbon chain on one side and 5 carbon on one side. So clearly it's an unsymmetrical anhydride. So we're going to need to name both of these chains. So let's think about what the parent name is, right? So we're going to have 2 parent chains. So we have, what do we have? We have, so the blue one is 1, 2, 3, 4, 5. It's pentanoic acid, right? But instead of the acid, we're just going to put anhydride because it's an anhydride, right? So just name the carboxylic acid. And also number it where the double bond is. It's at the second, so we do 2 pentanoic anhydride, right? And you could number it also in the middle, like over here, the 2. It's just up to you. I just like to do it in the beginning. Okay, whoops. So anhydride, and let me get rid of this, so make it cleaner. So yeah, so 2 pentanoic anhydride is the blue chain, and the red chain is 1, 2, 3, 4. So it's a butanoic acid. You get rid of the oic acid and you add anhydride. So it's going to be butanoic anhydride. Okay, on the left hand side, the red one. Okay, and let's think about what are the subs that we have, substituents. We just have one substituent. It is this methyl group that's hanging off this this 4-carbon chain. So we're gonna name it 2 red. So 2-methyl. Okay. No other substituents. And then last bit is think about what is the stereo we have. So the only stereo we have is in this double bond. It's gonna have either you can do trans or cis or E or Z. Okay, so I'm gonna do E and Z. So let's see what we have. Do we have E or Z? So let's draw out the hydrogens so we can see. Okay, so we have this one. This is the high, like higher mass, so it's pointing down, and this higher mass is pointing up. So we have down, they're pointing in opposite directions, so that means it is the stereo is E. Okay, because remember Z means same side. Okay, so Z is same side and E is opposite side, so it's a E. Also, you could name it also trans because the hydrogens are trans, so that's also acceptable stereochem. Either one is fine, either E or trans. Okay, so now we have all the components. Let's combine them into one name. Okay, so what are we going, so what you want to do is the subs. So I put the sub in red because it goes with the butanoic anhydride part, right? So we're going to put let's put 2-methyl butanoic okay, and we're only going to use one of the anhydrides. We don't need to put anhydride twice, so we're just going to put it at the end. Okay, so then we go to the second chain is the pentanoic anhydride, and this one is the one that has the E stereochemistry. So we're going to put E here, then we're going to put 2-pentanoic, let's keep going, pentanoic, and now we're going to put the anhydride part at the end. So anhydride, so a very long name. Okay, so we have 2-methyl, so 2-methyl butanoic E, 2-pentanoic anhydride. Okay, and the important bit to keep in mind is think of when you have unsymmetrical anhydrides, think of it like you're naming two separate compounds, right? So you have, this is the first compound, 2-methyl butanoic, and then this is the second compound, E2-pentanoic. And the anhydride bit you add at the end always, okay, if it's an anhydride. And so why that's important is if it has any stereochemistry or any subs, you keep it with that with that chain. So in this case, we wouldn't put usually we put the stereochem at the beginning, but when you're naming anhydrides, you don't want to do that. You want to keep the stereochem with the chain that it corresponds to, right? So the E, the blue chain, the pentanoic anhydride, the pentanoic chain, that's the one that had the E stereochem. So that's why we put it in front of that. And then this butanoic, this is the one that had the 2-methyl. So that's why we put it with that. Okay, so keep that in mind. It's a little bit tricky, but just think of it like you're naming, it's like two nomenclature problems in one. Okay. Okay, so yeah, so that's the name of that. Let me highlight it so you know it's the answer. Here we go. Okay, let's look at the next one. So first bit is always figure out what type of compound do I have. So I see here is a double bond O, and I also see an oxygen. So you might be thinking this is an anhydride, right? It has all those components as the anhydride should have. But this is not an anhydride, okay? this is in fact a ester. And the reason why is because if you look, the reason why it's not an anhydride is because anhydrides need to have this form. The oxygen needs to be in the middle of the two carbonyl groups, right? And then you have R groups attached. But in this case, the oxygen is not in the middle. It's actually to the left of one of the carbonyl groups. So this is why this is not an anhydride. If the oxygen was here, then it would be an anhydride. But that's not the case. So what is this compound? It's an ester because if you remember, esters, they have this form. RC double bond O, OR. Okay. And this is exactly what we have. We have R is here. Okay. C double bond O is there. And O, and then another R. So these are the components. And why we can't recognize, why it's difficult to recognize right off the bat it's an ester, it's because they added this carbonyl group here. But don't get confused, just circle, just sort of keep in mind what it's supposed to look like, right? So we have, this is an ester, okay? And so let's see so let's start naming with the parent. So zoom in a little bit so we can focus on this. Okay, so parent will be the bit that's attached to the right of the carbonyl group. So this will be the parent chain, okay? Because the O, whatever is attached to the O, that will be named as a sub. So let's first name the parent chain. So parent chain we have, let's number it. So, So we have 1, 2, 3, 4, 5, 6. So we have a 6 carbon chain. That means we have, if we name it as a carboxylic acid, we have hexanoic acid. And remember, for esters, we get rid of this ic acid part, and we put 8. Okay, hexanoate. Okay, so just to keep that in mind, now let's actually write it like that. And one thing I'll do is, we also see that we have this substituent group, and since the substituent is attached to this chain, I'll name it I'll name it here with the parent chain. Okay, so the substituent is a carbonyl group, so, and it's a ketone, so you would name it oxo. Okay, so 3-oxo, and we got hexanoate. Oops, hexanoate. So you could put the 3-oxo part when you're naming the subs, but I just like to do it here because it is part of the parent chain. So just get it over with. Right, okay, let's number it. Okay, so that's the parent chain, 3-oxo hexanoate. Okay, now let's look at what is this other bit. So what we have here is, let's number it first. We have, okay, so I'll do it in red this time. So we have 1, 2, 3, 4, and then an oxygen with a methyl group attached, a methoxy group. Okay, so the subs would be, the substituent group is, so you have a 4-methoxy, right? This bit is a methoxy group. So 4-methoxy, and then this you name as a alkyl group. So 1, 2, 3, 4, that's butane, so butyl. Right. So name it as a substituent. So 4-methoxy butyl. And then stereo, we don't have any stereo in this one. There's no stereo center or any double bonds. So stereo, none. So stereo, we have none. Okay, so let's combine all of this, what we have down. So this is a real easy one, we don't need to think a lot now. So the subs, we put the subs 4 methoxy butyl and 3 oxohexanoate. 3 oxohexanoate. Okay, so that's the name of that compound. Alright, so hopefully understand how to do that one. Also, let's highlight it so we know it's the answer. There we go. Okay, and the last problem we have for the stereochem. So what kind of not stereochem, for nomenclature. So what kind of compound is this? Well, let's think. So it is a carboxylic acid derivative because we have C double bond O there, and we have an N attached to it. So that tells us it's an amide. Okay, it's an amide. So now let's think about how do we name amides. So let's start with a parent chain. So parent. So the parent chain will be this bit to the left because it's not the bit, this N part, that's going to be like a substituent. So that's not the parent chain. The parent chain will be here. So 1, 2, 3, 4, 4, 5. Let me change that 4 better. So 4 and then 5, right? Oh, my bad. See, this is where it can get, you want to be really careful. So you want to start naming, numbering at the carbonyl. So 1, 2, 3, 4, 5, 6. So the carbonyl carbon, it's always going to be one of the carbons. Okay, so you need to include that. So always be careful of that. You don't want to do what I just did. So it's actually a 6 carbon chain. So what's the parent going to be? It's going to be, and it's alkene, right? So it's going to be hex, 2 hexene, because it's at 2. The double bond is at the second carbon. So 2-hexenoic acid, that's the carboxylic acid name, right? But for amides, remember you get rid of the oic acid and you add amide. So what we have here is 2-hexenamide. Okay, so let me write that. So 2-hexenamide. Okay, and then let's think about what are the subs we have. Subs. So the subs we have, let's highlight them. So we have this, we have this, and we have that. Okay, so we got 3 subs. So let's name, let's see, think about what the names of these subs are. So remember the nitrile group, it can also be a substituent because it's less priority than the amide. So that's why in this case it is a substituent. So how you would name it is 3-cyano, right? So this is not like a nitrile compound because the nitrile is lower in priority than the amide. So the nitrile becomes a substituent. So it's named 3-cyano. Okay, and then these ones, remember the ones that are attached to the nitrogen, we don't put a number in front of them. We label it as N, and then what is the name of the R group. So N, one of them is a methyl, and the other one is an ethyl, right? Because it's a carbon there, over there, and 2 carbons, so it's an ethyl. So we got, let me highlight it again. So we have N-ethyl. Okay, so N-methyl, N-ethyl, and 3-cyano. We got 3 substituents. So, and then the last bit is the stereochem. So what do we have for the stereo? Do we have any stereo? Yes, we do. Because if you look at here, this is the double bond. It's in the middle of the chain. So we do have some stereo at this double bond. So either E, Z, E, or Z, right? And this time it won't be cis or trans because there's no 2 similar groups attached to them, right? So let's see what the stereo will be. Is it going to be E or is it going to be Z? So let's highlight the higher molar mass group. So we have this is higher and this is the high. Okay, because this is going to have hydrogen attached here. So that's definitely low. So high, they're pointing up on the same side. So that means same side means Z. Okay, so Z. So the stereo is Z. And you could put 2Z, like label it which carbon it's at. But since there's only one double bond, we don't need to do that. Okay, so let's combine everything into one final thing, final name. So we have, so we'll put the stereochem first, Z. Okay, and then we have these 3 substituent groups. So which one do you put first? Well, you need to put them in the alphabetical order. So we have Z, 3-cyano, because C is before N. C is before M or E. So 3-cyano. Then we have N. Ethyl will go before the methyl one. And we have N-methyl. And then we have the parent chain name. So parent chain is 2-hexenamide. So 2-hexenamide. Okay. So there is our name, very long name. Z, 3-cyano, N-ethyl, N-methyl, 2-hexenamide. Okay. And let's highlight it. So what was important to keep in mind in this one is that it was a substituted amide, so you need to number the amides as with the N instead of like normal numbering. So that's that one. Okay, so these were all the ones we covered. Now let's go over to the reaction section. Okay guys, let's go ahead and get started with the reaction section. And before we move on to the reactions, I would just like to mention that when I was doing the review for the carboxylic acid derivatives, I did forget about the acid halides. So here I just added this so we can briefly go over it. So for acid halides, follow the same technique, name the carboxylic acid. So we have a 4-carbon carboxylic acid, so it's butanoic acid. Get rid of the ic acid part and add YL, ill, and then whatever halogen is attached, name that halogen at the end. Okay, so in this case it's a chloride, so we would name it butanoyl chloride. If it was a bromide, you would name it butanoyl bromide. Okay, so the main thing is this YL bit. This is what you need to remember to add instead of the ic acid for acid halides. Okay, let's move on to the reaction section. So let's see what we have first up. So first reaction we have is a anhydride, cyclic anhydride, with a the first step is a secondary amine, right? So I always like to put down like what am I reacting, because it does help if you memorize or learn the reactions this way, like what type of compound with what gets you what, right? So if you don't, if that's not how you remember it and you just like to get into the mechanism, then that's also fine. Okay, so the first step will be that this lone pair, I'll do the mechanism just to make it clear. But what it's going to form is a tertiary amide. Okay, so anhydride plus secondary amine, it forms a tertiary amide. An amide, remember, it looks like this: C double bond O, N, and tertiary means it has two R groups attached. Okay, so that's what's the final product of this going to be. But we'll do the mechanism just for practice, right? So first step is anhydride, the lone pair on the nitrogen, gonna come attack one of these carbonyl carbons. It can be this one on the bottom also, they're both the same, it doesn't matter. But what matters is you attack like the carbonyl carbon, you don't attack any other carbons. And then this electron pair is gonna get kicked up. And so we are tight on space here, so let's zoom in a little bit more if we can. Okay, so what's gonna happen is this is not the final product of that what just happened. It's gonna be like that, like this, double bond, this like the intermediate stage, like that, and we have this NH with the two methyl groups attached, and the NH is gonna have a positive charge. Okay, the oxygen is gonna have negative because it got those lone pairs, and the nitrogen has a positive charge. Okay, formal charge. So the next step will be to get rid of this positive charge on the nitrogen, and how we do that is we deprotonate it. Okay, so what you might be wondering, what deprotonates it? Well, we have another one of these amines in the mixture, in the like solution, so it's just gonna come in CH3 to NH. So this lone pair is gonna come in, it's gonna attack the hydrogen, and those lone pairs from the hydrogen will be kicked off to the nitrogen. That's a little bit messy, but it's not the mechanism section, so we just need like the shorthand way. Okay, so let's move it down a little bit. So we have this, we got that, and the oxygen still has a negative charge, and it doesn't have H anymore, we deprotonated it. So now it has become like almost in that final form we discussed earlier, like the tertiary amide. So then this electron pair is gonna come down and then kick off this bond to the oxygen. Okay, so it's gonna be like a ring opening. This is still step one. So long step, but then the other steps will be faster once we see what happens here. So got this on the bottom, and now this has become a O minus, and this has become a double bond O, and this has become a tertiary amide, right? So this bit is the tertiary amide that we were supposed to get, right? And then the second step of this is, so this was all step one, what I just did, right? I think I'm gonna need to keep going like to the right. Yeah. So let's do step number 2 is H plus. So the H plus is just gonna protonate this O minus and make it a OH group. So what's gonna happen is this will be like that, like this, like that, and those two methyl groups. Okay, so basically in a cyclic, if you have a cyclic compound, you will form like two different functional groups. So we form the amide, the tertiary amide, and we form the carboxylic acid. So we formed two functional groups because of the cyclic nature of the compound. Okay, so the next step is SOCl2. on step number 3. So let's check the ones we've done. So we've done 1 and we've done 2. So let's go to step number 3 is the SOCl2. So what that does is it's gonna make the carboxylic acid into a acid chloride, right? So keep this bit the same, the amide bit, and it's just gonna react with this part and make it a chloride. Okay. Then next, what do we have? We have CH3CH2OH. So what that does, this is like a kind of like a Fischer, kind of Fischer, kind of not Fischer, but similar. The product will be similar. So what's gonna happen is instead of this chloride, we're gonna have a ethoxy group, right? And I'm not gonna do the mechanism just because that will be covered in the mechanism section. But what's just gonna happen is this chloride will be replaced by a ethoxy group. Okay, so like this, yeah, and it won't react with the amide, only with the chloride because the acid chloride is more reactive. So here we go. The amide bit stays exactly as it is. Then let's check number 4 off. Then we have LiAlH4, right? So this is the reducing agent. So that's gonna, it's a strong reducing agent. So it's gonna reduce everything. So the amide, let's go here. Let's go here. So the amide, it will be reduced to, so this carbonyl group, it will be reduced to a CH2. We will get rid of the carbonyl, okay? And the ester at the bottom, it's going to be reduced to a primary alcohol, okay? So what's going to happen is, got this, and instead of the carbonyl, we're just going to put nothing there because it's been reduced from the LiAlH4. Oh yeah, this is also step 4. And now we have step 5 and 6. 5 and 6 are together. And then we got on the bottom, we don't have that. We have a primary alcohol. Okay, so primary alcohol meaning everything is gone and it becomes like just the OH. Okay, this carbonyl carbon stays. This carbonyl carbon stays, but everything else, it's reduced and it becomes OH. Okay. So, any other steps? No. So this is step 5 and step 6. We are done. And so our final product is gonna look like this. This is our final product, what we got. So N, like that, and OH. Let me draw it a little bit cleaner so it looks better. But yeah, so just keep in mind when you have cyclic anhydrides or any cyclic compound, when it ring opens, it's gonna form like 2 functional groups. So there's gonna be more like different types of products that can be formed. So here we go. So that is our final product, that compound. Okay, and let's go on to the next one. So the next one is kind of like a retro synthesis type question because they've given us the product and they've given us they have also given us the reactants, okay, the steps. So we just need to find the starting material. So if we notice, let's start off with the last reaction that we do before we get to the product. So what is this kind of compound characteristic of? This is a Wittig reaction. Okay. So this tells me we have so in a Wittig reaction, what happens is you have a carbonyl compound and a Wittig reagent that has this pH, so this 3 phenols, phosphorus, and whatever R prime group. And what happens is you replace this carbonyl group with the double bond R prime. So you'll form something like this in a Wittig reaction. Okay. So that, but it's more complicated than that, but this is the reaction section. So we just need to know what each reaction, what the product we get, right? So in the Wittig reaction, if we step back, we notice that this double bond CH3 bit, this is what was added by the Wittig, right? Because see here, double bond CH3 and 2 CH3s, that's that exact same thing, right? So what that means is we started with this CH3 C triple bond C CH3, and then here where we added that double bond CH3 2, we would put the carbonyl, right? Because that's what happens in the Wittig reaction. The carbonyl gets substituted or replaced by the alkene. Okay, it allows us to put double bonds in specific location where the carbonyl is. Okay. Then next step or second last step. So we'll say this is number 4. So number 3. So what did we start with? So remember for PCC, what you need to have is an alcohol. So in PCC, an alcohol is PCC is an oxidizing agent. So alcohol gets converted to either a ketone or an aldehyde. Okay. So what you'll do is this group here, the C double bond O, it will become alcohol. Okay. So CH3 COH, and copy the other part of the compound stays the same, CCH3. Okay, so you see here the alcohol, it just became oxidized to the C double bond O by the PCC. Okay, and then this next step is kind of like a combination of, so these two are combined, 1 and 2, because in 2 what's going to happen is 2 is going to be, see it's a H3O plus, so it means this oxygen is going to get protonated. So it means we started with a CO minus before, right? Triple one CH3, like that. So this is step number 2, but technically 1 and 2 are like combined. It's kind of like the Grignard kind of reaction. Okay, but you notice here, what is this? This is a nucleophile, right? So CH3, the alkyne, is a nucleophile, so it's gonna attack something, and it's gonna form an O minus. So what is the reaction that we know that does that? It's the one with the carbonyl, right? So it's gonna, this is gonna attack the carbonyl, and it's gonna kick off those electrons. That's how we get the O minus, right? And so that means we start off with an aldehyde. Okay. Okay, let's get on with the third reaction. So let's see what we got. We have a hexanone compound, and then the first step is we're treating it with Br2 and acetic acid. So this is a alpha bromination. So bromine will be added to the alpha carbon. Okay, so what will happen is you have this alpha carbon or this one, and you can pick either one, and just add the bromine to one of those carbons. Okay, so we have O and Br. Okay, so that's the alpha bromination. Then next step is we have the pyridine. So it's a bulky, strong base. So that what that tells us is it's an E2 reaction. So what's gonna happen is the hydrogen is gonna get here. Let me draw the base. Okay, so it's gonna get eliminated, and these will get pushed down, and this will get kicked off. Okay, so that's the E2 mechanism basically. So what you're gonna end up with is a double bond or an alkene at this location. Okay, then the next step is you're treating it with this weird compound and heat. But if you notice, so let me draw it like, okay, let me just draw it like that, that's fine. But if you notice, what does this remind you of? This is a Diels-Alder reaction. Okay, so you have, this is your dienophile over here. Okay, and this second compound, this is the Diels, this is the diene. Okay, so we have a diene and a dienophile. Okay, so be sure you can recognize like these type of structures. Whenever you have like two double bonds in this form, and then a single bond like this in between them, it's a diene, and a dienophile is like a double bond or triple bond, and you have electron withdrawing groups. Okay, so this, like in this form, we don't usually see it like this, so let me draw it how we are used to seeing this diene and dienophile. So this is like that, right? So I'm just turning it over so we can see how the mechanism goes. And then the dienophile will be like, I'll just flip it over like that, right? So what happens in a Diels-Alder is this double bond come here, this will come to this carbon, and this will go to that carbon. Okay, so you form a bicyclic structure. Okay, so what you get, and what's gonna happen is this is a cyclic diene, right? So these are gonna get pushed up. So it's gonna be like a bridge, right? So usually when you don't have that, then you don't need to worry about it. But in this case, we do have a like a cyclic diene. So those two bonds are gonna get pushed up to form like a bridge. So it's gonna end up looking like this. So we draw it in this conformation. So you have the 6-membered ring that you just formed, right? And then these are the two highlighted yellow bonds that got kicked up into the bridge. And then the dienophile you will draw like that and like that, and we have a OCH3 group attached here, and remember the double bond is here. Okay, and then also with these you have to worry about the stereochemistry, right, with the Diels-Alder reaction. And remember, the dienophile, it prefers to be in the endo position, which means the dash. Okay, so it's gonna be hard to like show how the like dashes on this. So what we do is just put hydrogens on the wedge, right? So we'll put hydrogen wedge. That would, so what that means is then that this whole group is on a dash, and that's what we need to just indicate, right? So just put hydrogen on, and then you might be wondering, well, what about this stereochemistry for the group attached on the diene? We don't need any stereochem because this is a double bond, right? So it doesn't have, let me make sure it doesn't look like a wedge. Yeah, so we don't need any stereochem there because this is a sp2 carbon, so it's all planar, right? And yeah, so this is how the final product will look. So let's draw it in the box. So we got like that, the bridge, the double bond, the OCH3, and then we have the dienophile part, and we put the hydrogens on the wedges to indicate that the dienophile, the electron withdrawing group, is on the endo position. Okay, so this is how our product looks. Alright, so this was like a good example because it covered an old reaction, the Diels-Alder reaction, and some of the new reactions, the chapter 22 things, the alpha bromination. Okay, so just keep this, be able to recognize the diene and dienophile structures. So when you do encounter them, you know what to do, right? Okay. So next, let's see what we have. Okay. So we have, first step, what we notice is this is the Gilman reagent, right? So what the Gilman reagent does is it forms a ketone. Oops, spelled that wrong. Yeah. what the Gilman reagent does is it forms a ketone from either a carboxylic acid or an acid halide. Okay. So in this case, we do have an acid halide. So the Gilman reagent, the step 1, will be forming, instead of this chlorine group, we will attach the CH3, one of the ethyl groups. So we get this CH2, CH3, and then this methyl group stays, right? So, and a common mistake with the Gilman reagent is you see this is like two equivalents of the ethyl, like 2 ethyls. So you might think, oh, I need to add 2 ethyls instead of the 1 ethyl. But don't do, the Gilman reagent is a weak reagent, so it only adds once, right? This is why we use it, this is why it forms the ketone. And it's different from the Grignard reagent because if we use the Grignard here, it would add it twice. It would add those 2 ethyl groups because it's very strong. So it will keep attacking the carbonyl. But the Gilman, it's a weak reagent, so it will only attack it once, and then it's too weak, so it won't attack the carbonyl one more time. So that's why only 1 ethyl group is added, right? So only one of the ethyl groups is added. Okay, then the next step is LDA, and LDA is a strong base. It's a bulky base. So what that will do is it eliminates the alpha hydrogen. Okay, it deprotonates the alpha hydrogen. So the key step here is to recognize, well, which one is the alpha hydrogen, right? So if we look at we need to first see where the carbonyl group is. So it's over here. So it can either be on this carbon. This could either be the alpha carbon, or this one could be. Okay. So the which one is the alpha? It might seem like we have two choices, but we actually don't, because this carbon, this doesn't have a hydrogen, because it has 1, 2, 3, 4 bonds already, right? So it doesn't have a hydrogen, so it can't have an alpha hydrogen. So what that tells us is it is this one of these hydrogens that we need to deprotonate. So what we'll have is we will deprotonate that alpha. Let me put alpha. Yeah. So we'll put alpha, and so we get that CH3 stays. We depronate it so it forms like a carbon ion, and CH3. Let's put a minus charge. Okay. And the last step is just it's a SN2 reaction. So this negative charge, it will attack that carbon and kick off the bromine. So what we will get is this. So let's go here. C double bond O stays, and we get CH3. So that's that part, and then we'll add the extra bit that we got from step 3. So CH2, CH3. That's what we added, the ethyl group. And don't forget about the CH3 group here. And put it on a dash, since it was on a dash originally. Okay, so that's the final product. So let's draw it in the box. So what we will get is this. Got that CH3. We have the ethyl group attached to the top. And we got the methyl group that was untouched from the beginning. Okay, so that's our final product. Let's box it in. Okay, let's move on to number 5. So first is write down what type of compound we have. So we have a nitrile that we are starting with, right? And what is our first step? We are reacting with H3O plus at a very high temperature, 200 degrees Celsius. So nitrile plus H3O plus, that tells us we're gonna get a carboxylic acid, right? So let's see what we get from step 1. Got the carboxylic acid, like this, right? So this is acidic condition, so this H, it will stay, it won't get it's not deprotonated. But if it was, keep in mind, if it was OH minus at 200 degrees Celsius, this can also hydrolyze the nitrile group, but it will end up with this. You would end up with this, like negative charge on the O, because the OH will deprotonate the H. Okay, so you would need to add like a H plus, but we don't have that, so we don't need to worry about it. So yeah, so H3O plus 200 degrees Celsius, this is a hydrolysis reaction, and it will make the nitrile group into a carboxylic acid. Okay, next we have a ethanol and H in acidic conditions, H plus, and we have a carboxylic acid. So what that means is this is a Fischer Esterification. Okay, so this is Fischer. Okay, so we could go through the mechanism, but it's pretty lengthy, so I will just put what the final product is. And for Fischer, the final product is easy to get. what you will do is you will just form, it's in the name, Fischer Esterification. So it means you form an ester, right? So what happens is, this OH will get replaced by this ethoxy group. So you will get, as the product, you will get this OCH2 CH3. Okay, so for Fischer, if you see it in the reaction section, it should be really simple. Just replace, it can be a carboxylic acid or a acid chloride. Just replace that OH, or if it's acid chloride, the halogen, with a acid halide, not chloride. But usually it's a chloride. So just replace the halogen or the OH group with the OR group. Okay. In this case, it is ethoxy group, so we replace it with that. So step number 3 is gonna be one of the chapter 22 reactions, right? Because this is NaOET ethanol. That's a characteristic reagent of either aldol, Claisen, Stork, or Michael. So let's see which one of those it's gonna be in this case. So remember, we have aldol, Claisen, Stork, and Michael. Right. So for aldol, we need the starting material is going to be aldehyde or ketone. So we don't have that. This is an ester. So nope, not aldol. For Stork, we need we also need an aldehyde or ketone. But for Stork, we also need like we don't use the NaOET ethanol. We use we need to first form an amine. So it also has, like, you need to form an enamine in Stork. Or yeah, so you need to form an enamine in Stork, but we don't have any of those steps. We don't have any nitrogen steps to form the enamine, so we know it's not going to be Stork. For Michael, you need a acceptor, a Michael acceptor, and a donor, right? But we don't have two compounds. We just have this ester that we got. So what is going to be, let's say, what is going to be the Michael acceptor? Well, we don't have, NaOET is not a Michael acceptor, right? So that's why it's not going to be Michael either, because there's not one acceptor, one donor. We only have one thing. So what that tells us, so Claisen, what is Claisen? Well, the starting material for Claisen is an ester. Okay. So that's why it must be Claisen. Okay. And but let's say we didn't know it was, we don't know what type of reaction it is. We don't know like the name or whatever. What you can do with all these type of reactions is just start off by doing the mechanism, right? And then just see where it takes you. So in the mechanism, what happens is NaOET, this will come in and deprotonate. It always deprotonates the alpha hydrogen, except in Michael. But it's going to deprotonate the alpha hydrogen. So what happens is it'll look like this. Right? So the alpha hydrogen is deprotonated. Oh, wait, let me put it like this instead of, it's a little bit wrong. But yeah, but this is a reaction, so you can be a little bit quick with it. But you know it's going to get deprotonated. And then the next step is going to be, there's going to be another equivalence of this compound of this ester in the mixture. So what's going to happen is this act as a nucleophile and attack this partially positive carbonyl carbon, kick those off, and this is just shorthand. This will come down, and this ester, this ethoxy group, it'll get kicked off, right? So what we will form is this. So I'm gonna draw it from the alpha bit first. So this is the alpha hydrogen. So alpha looks like this. Got the C double bond O, O, CH2, CH3, right? And then up here I will add all of this new compound. So we got C double bond O, and we have this, and we have, and that's it. Yeah, that's all we have. And the last bit is gonna be to what is the last bit? It is step number 4 is, so this is what we get from step number 3, right? And it looks a little bit weird, but here, let me try to draw it so it looks a little bit cleaner, how the compound is supposed to look. So it's gonna look like this. So C double bond O, and then like that, and like this. Yeah, that looks right. And then this ester group is coming off of it, right? So this is just the same molecule, just drawing it a little bit cleaner so we can see for the next step number 4 how we need to what we need to do. Okay, so step number 4 is H3O plus and 180 degrees Celsius. So that what that does is it's gonna get rid of this ester group. Okay, so it's just gonna get rid of that. So what we're gonna end up with is number 4 is gonna be, if we draw it like so, and I'll do that all line angle, and we have double bond O in the middle. Okay, so that's what the final product is gonna look like. Okay, so if we were going off of this structure, what would happen is this ester group is gone. Okay, so it'll end up being a C double bond O and 2 benzene rings attached, okay, in a symmetrical way. So this will be our final product for this number 5 reaction. Okay, a little bit tricky, but what I would say is try to understand like what as I was saying earlier, like what are the starting materials for aldol, Claisen, Stork, and Michael, and what are the end products also, right? So for Claisen, the end product, this was the product of the Claisen reaction, right? And then we treat it with H3O plus to form that. But this was the Claisen product. And the Claisen product is a beta keto ester. Okay. So we see here alpha beta. So it's a beta keto ester. So or you can think of it like there's 1 carbon in between the 2 carbonyls. Okay, so for the last reaction, we have in the first step a ketone with a Grignard reagent, right? CH3 MgBr. So what happens is the Grignard will attack the carbonyl like always and kick out the electrons to the oxygen. So step 1, we will get this O minus, oops, and CH3. Okay, and an important note on this one is it is gonna stay in that O minus form. It's not gonna be OH, even though we know, because usually in Grignard we expect it to form like an alcohol at the end, but that's when they say like then H3O plus. But you don't have that in this. They just have step 1 is the Grignard reagent. So Grignard reagent, it does not form the alcohol. You need to put then H3O plus, but we don't have it, so we will form like the negative oxygen. Okay, the deprotonated form. So keep that in mind in case you get like a question that says it's attacked by a Grignard and it doesn't say then H3O plus, and it asks for what the like intermediate product is, then it's gonna be with the O minus, the deprotonated form. Okay, and step number 2. So this is where it will get the OH, the O minus will get pronated by the H2SO4, right? Because the H2SO4 is a strong acid, so it can donate H pluses. So this is where it becomes like the tertiary alcohol. And then this is a dehydration, H2SO4 and heat, sulfuric acid and heat. This is dehydration reaction. So what happens now is the OH will get pronated again, okay, by the HSO4. So we will get a good leaving group, H2O. And then we need to eliminate one of the hydrogens and push it down to become a double bond, right? Form an alkene. So, which hydrogen do we eliminate? Well, we have a couple of options. We have this one here, we have this one here, and we have one of these ones. Okay, so which one is it gonna be? Well, in this case, it's gonna be this hydrogen here. And the reason is because we want to form the most substituted alkene. Okay, if we eliminate one of these ones, either this one or this one on this carbon, we're gonna form a disubstituted alkene. But if we eliminate the one we're supposed to eliminate, we will form a, how much is gonna be, 1, 2, a tri-substituted alkene, right? So more substituted alkene is better because it's more stable. So what's going to happen is the HSO4 minus is going to come in, take that H, push down those, and we formed a good leaving group, so that leaving group will leave. Okay, so the product from the second step after all that, it's going to be this. Okay, so we have the two methyl groups, this methyl group and this methyl group, which are here and here, and we have this methyl group, which is here, right? Okay, step 3 is MCPBA, one of the easiest reagents to remember. So this is, it will form an epoxide, right? So this alkene is going to turn into an epoxide, and be sure to keep the stereochem the same as you have in the original thing. Well, it doesn't matter that much because they are all methyl groups, but just keep in mind when you turn it into epoxide, keep the same stereochem as in the alkene, right? So if it's pointing down, keep it pointing down. Okay, step 4, we have attacking with an alcohol here, alcohol and acidic conditions because it says the H plus. So here the thing we need to remember is the BLAM acronym. So basic, you attack the least substituted side, and acidic conditions, you attack the most substituted side. So we have acidic conditions, so we're going to attack most substituted side of the epoxide. So is it going to be this one or that side? It's going to be this one, right? Because this has two R groups and the other one has one R group. So most substituted is this side, right? So what's going to happen is the CH3, CH2, OH, so the electrons come in, attack that carbon, whoops, and then kick it off to this. The epoxide will be opened, right? So what we'll end up with is something like this. A little bit difficult to draw, but I'll try to draw it. OCH2, CH3, and H. This will have a positive charge. And this is just the mechanism. This is not the final product, okay? I'm just drawing this mechanism out because this is one of the older reactions, so just to remind you guys how it works. Alright, so this one, the O, it will have the O minus, and this, it'll have CH and CH3. Nice methyl group, right? So now what will happen is there will be more ethanol, like there's ethanol or the H plus in the mixture. It will protonate this oxygen, and the ethanol will deprotonate this hydrogen. So the final product will be something like this. This is still step 4, okay, but this is the actual final product of step 4. That was like the intermediates. So if we draw it like this, so this hydrogen is gone. It was taken by one of the ethanol molecules, and this O minus, it can get protonated by the ethanol or by the H pluses, since it is acidic conditions. So it's not going to stay O minus, and we have CH3. This methyl group stays as it is. Okay, so what we have is this, the final product. So funny looking product, but just follow like the mechanism steps and you should be able to get to this final step. Alright guys, that will be it for the reaction section. I know this was not all of the reactions that we need to know. There is a lot, but it was a good chunk of them. So the ones that we did not cover, you guys can review on your own. So keep practicing, and good luck on the exam.
Hello guys, good evening. This is Danny. I'll be going over mechanism, synthesis, and spectroscopy, in addition to a couple of multiple choice questions from the ACS booklet. So starting off with the mechanism. She's asking us to provide a clear mechanism to explain the information of the product, use curved arrows to indicate electron flow, remember to show only one step at a time, and show all intermediates and all formal charges. When more than one resonance contributor may be shown, be sure to draw the most stable contributor. Alright, so first thing first is what I like to do here is I look at the reagents, and we can see that it's a base and we have ketones. We know from the last couple of chapters that this type of reaction is a condensation reaction, and this base is going to grab the most acidic hydrogen. In addition, we can also tell that this is going to be an intramolecular reaction, meaning that one of those hydrogen is going to react with the same molecule to create that product. So now first thing first is we have to determine which hydrogen are we deprotonating, right? So we know that there's no hydrogens here, so we can't do anything here. So but we have a hydrogen here. We have a hydrogen here, and we have a hydrogen here. Now, in the mechanism process, it's really easy to do that because they give us the product. However, if it was a reaction section, the fast way to determine this is you want to avoid having a 3-membered or a 4-membered ring because those are unstable. However, in this case, we know that this carbon is the same as this carbon, and we can see that we formed a 1, 2, 3, 4, 5-membered ring. Well, it's 2 fused cyclohexanes. Now, if I deprotonate this hydrogen, I'll have a 1, 2, 3, 4, 5, 6, which is similar to what I have here. Right, so this is how I was able to determine that this is the hydrogen I have to deprotonate, the alpha hydrogen I have to deprotonate. The other thing that also I should mention here is that once we deprotonate this hydrogen, it's going to attack the carbonyl carbon, which is partially positive, and I'll go over that in more details right here. So the first step is that this base is going to come in, you grab the hydrogen and forms a carbon anion. And it will look something like this. So we have the double bond. We have the double bond O. 2, 3, 4, 5, 6. Double bond O. Now we have a carbon anion right here, and we have this carbon right here. Now, the second step is gonna be, before we do the intramolecular reaction, we have, remember what she said, we have to draw the most stable contributor of the resonance. So in this state is we're gonna resonate. So it's gonna resonate. This will form a double bond, and then we'll attack right here. So now we have 1, 2, 3, 4, 5, 6 with an O minus and a double bond O. Now some people ask here, like, even though like this will look more stable, right? But if you guys remember in the tautomerization, in basic condition in this case, you gotta always keep in mind that the ketone form of the tautomer is more stable than the enol, and that's why we'll use this resonance structure to attack the carbonyl carbon. So the next step that's going to happen is that negative charge is going to attack the carbonyl carbon and form the O minus. Well, I'm not going to draw the O minus yet. I'm just going to draw the arrows. And again, how I like to do it is I like numbering everything. So that will be 1, 2, 3, 4, 5, and then 6. So now let's draw the next structure. So we have the 6-membered ring, where this carbon will have a methyl group, and this carbon will be number 5, 6. And drawing the other structure of it. So that's going to be my carbon number 4. Now carbon number 4, 3, 2, and 1. So we know on carbon number 1 there is a carbonyl with a methyl on the side, so a ketone. And we also know that on carbon number 6 there was a carbonyl that formed an O minus, so that would go right here. So am I missing anything now? I don't think so. So now, what the next step is going to happen is this O minus is going to grab a hydrogen and form an alcohol. So let's use pink again. It's going to grab the hydrogen from the ethanol and then form an alcohol. We have a benzene ring here. I mean, not a benzene, a cyclohexane. There's the methyl group here. There's the ketone right here. And now this O minus is now an OH. Now the next step is going to be the dehydration reaction. And the dehydration in this step happens because there is a presence of heat. If there was no presence of heat in this type of reaction, there won't be a dehydration. However, if the formation of the alkene will make it more stable, so for instance, if we have something like the benzene ring, right? And then we have like an O minus here, or an O minus right here, right? if you form a double bond right here, it's super stable. So this is favored even though there is no heat. If something is like, will form a bond that's the double bond that's conjugated with a benzene ring or another double bond, it's always this type of reaction will go ahead and finish all the way to dehydration even though there's no heat. However, in reactions that are not stable, such as this one, heat will be needed to form that dehydration reaction. So the next time is going to happen is the base that we had, ETO minus, is going to come in and grab the hydrogen, which is adjacent to the carbonyl, which is right here. Grab that hydrogen and it will resonate. So now we form double bond here and that forms an O minus. So now you have an O minus with a double bond. You have the other benzene ring right here, methyl, and that OH stays the same. Now the next time is going to happen, this O minus is going to get pushed down, the double bond is going to shift, and then the OH is going to get kicked. Again, the OH in this case is going to get kicked. The only reason to why it's going to happen is because we are in basic conditions. Remember, OH can be kicked in basic conditions as an OH, but it cannot be kicked out in acidic condition. If it was an acidic condition, you have to form H2O and then it's going to get kicked out. So the final product would look, I have to draw it. It's going to look something like this, with the double bond O right here, and then the double bond will be formed right here. And also, I'm pretty sure Anik mentioned it in prior reactions, but I'm gonna mention it one more time. Always when you're looking at the double bond in this type of reaction is an aldol condensation, right? In this type of reaction, the double bond should be formed between the alpha and the beta carbon, as you can see that. So this is a quicker way for you to be able to notice that this is a aldol condensation over a Michaels or Claisen, right? So moving on to the synthesis, this is a good synthesis, but I'm gonna change one thing. Well, there should be an F here, right? But you guys haven't done chapter 19, and this is a part of chapter 19, so I'm gonna change the F to a BR here. So the question asks us to synthesize the molecule below using any of the following reagents: a benzene ring, aniline, any alcohol of 4 carbons or less, or any inorganic reagent, any oxidizing or reducing agents, and any peroxy acids. So usually what we used to do in type of synthesis question is we look at the functional groups. Now in this case it's gonna be harder because there's a lot of functional groups. But we know that the last chapter that we learned is going to be aldol and Michaels. So what we have to look here at alpha and beta carbons, right? And how I do this is, so I know this is going to be my alpha carbon, right? So this is going to be my beta carbon, and this is going to be my gamma carbon. So if the addition is called, this is called a alpha gamma, right? I don't like to call it alpha gamma because it's a little bit confusing. I call this a 1,5. And the aldol is a 1,3, but that's just a personal preference. She likes to call it an alpha, like in the book they call it alpha gamma. So this is how I call it, 1, 2, 3, 4, 5. So between the two carbonyl there are 5 carbons, right? This is how I personally do it. You can just keep it as alpha gamma. So anyways, what's the point of this numbering, either alphabetical or numerical? Is to be able to determine if it's an aldol or a Michaels. If it's a 1 or if it's a alpha gamma, then it's a Michaels, and if it's a alpha beta, then it's an aldol. Now, we know that in both aldol and the Michaels, the bond that's gonna be formed is gonna be between the alpha and the beta. So I have to break it right here, or in this case, form it because we're going backwards. So if I'm going backwards, I know that this is going to be one of my structures right here, which is malonate, I think. I'm not really sure what the name of that structure is. That's the double bond O with the ester on one side, plus from the other side. So I know this is going to be my Michael donor. So Michael donor. And from the other side, this is going to be my Michael acceptor. And don't forget the double bond here. So this is one type of Michael acceptor. Right. So also the other thing that I want to mention is that always the carbon when you're doing in Michaels, the carbon that has the alpha carbon is gonna be the Michael donor, and the one that has the beta carbon will be your Michael acceptor. So just keep that in mind. And don't forget the reagents are gonna be 1, which is gonna be your base, NaOET, with the ethanol, and then you're gonna protonate it. Don't forget the protonation using H3O plus, or just put it in any sort of acidic conditions. So let's try to form the Michael donor first. So here we can use a Claisen condensation. So what it is, it's using 2 esters to form that bond. So again, it's the same type of aldol condensation, right? So what happens is you're just gonna need an ester with a double bond O, right? 2 equivalents of it. You don't have to write 2 equivalents, right? So it's gonna react with itself. That's one. See, so NaOET again with ethanol, and then you're gonna put it in acidic conditions. So what happens is you're gonna form, this is your minus, right? It's gonna attack another structure of the same molecule on the carbonyl carbon. This is gonna go up, come back down, and kick off the CH3CH2O, and then this will form this structure right here, right? I just want to go over the mechanism really quick. Now, to be able to form this ester, we can just use the Fischer Esterification, which combines the carboxylic acid and alcohol in acidic conditions. So that would be H, and then you put it with an alcohol. In this case, it has to be a 2-carbon alcohol, right? So CH3, CH2OH. And that would be in also acidic conditions, so there will be such an H+. And, you know, she said that you can start with 4 carbons or less of alcohol. So just, you know, you can oxidize a alcohol of 2 carbons or less in this case. So CH3, CH2OH. And in this case, you have to use Jones oxidant. Jones ox. Remember, guys, you cannot use PCC here because PCC will take it all the way to an aldehyde instead of a carboxylic acid. You want a strong oxidizing agent. You can also use Na2Cr2O7. So let me put or Na2Cr2O7 with acidic condition, H2SO4 sulfuric acid, and water. Alright, you can do that. Now, moving on to the Michael acceptor. So first thing first is we need to form that double bond right here, right? This is the easiest way we can start. Don't start by trying to form the benzene ring because, you know, that's the deactivating group, so we can't do really anything about it yet. So let's try to form that double bond, and we can just do an E2 reaction. So what Dr. Bean likes to use here is pyridine, or you can use like pretty much any strong acid like NaOET or anything, right? So having this double bond O with the bromine here. And so what you have to do, what you have to have for a E2 reaction is you're gonna have a bromine. Now the next thing is to be able to form that bromine. There is, you know, one of the new reactions you guys learned is Br2 and acetic acid, which will form a Br, which will add a Br group on the adjacent to a carbonyl group. So acetic acid. So now what you have is a benzene ring with a bromine. So now we have to go back all the way to, you know, the benzene ring reaction. So what we can do is we can start by doing Friedel-Crafts here. So we'll use a acid chloride, double bond OCl plus the benzene ring on the bromine, because remember, guys, the bromine ring is gonna act like an activating group and it's gonna direct it on a para or ortho positioning. So don't forget that reaction should be with AlCl3 as a catalyst, AlCl3. And to form that acid chloride, you put it with SOCl2 or POCl3 from a carboxylic acid, and then to reduce that, or well, we're going backwards, so to oxidize that and start from an alcohol, you can use Jones oxidant with 1, 2, 3, 4. So it's a 4 carbon, so that's good. So we can start with a primary alcohol. So 1, 2, 3, 4, that's good. Now to add the bromine, we can just do Br2 and FeBr3. On the benzene ring. Again, on the question that she asks, is they had an F here, because I know some people are gonna open the question that's on her 2016. It's an F. Don't worry about it, because this is from chapter 19, and you guys did not go over chapter 19. So moving on to spectroscopy. Alright guys, so looking at this one, we can see that the component she asks is C11H15NO. So first thing first is that we have to do the unsaturation number. And as we know, the unsaturation number that we've been using is the 2 times number of carbons plus 2 minus number of hydrogens divided by 2. But now we have nitrogen. So the unsaturation number formula is now equal to 2 times number of carbons plus 2 minus the number of hydrogens plus the number of nitrogens divided by 2. So in this case, 2 times carbon is 22, or 2 times 11, not 2 times carbon, is going to be 22, plus 2, which is 24, minus number of hydrogen, which is 15, and then plus 1, divided by 2. So as I said, 22 plus 2 is 24. 24 minus 15 is going to be 9. 9 plus 1 is 10, and 10 divided by 2 is 5. So from this we can tell that there is a benzene ring, right? Remember guys, the benzene ring should have a number of 4 or more, and we can also tell that there is one more that's probably a double bond or something. So looking at this, looking at the IR first, usually the NH structure has IR peaks between around 3300. So it should be like around here. It should have like, if it was NH, it would have just one peak. If it's 2 peaks, then it would be NH2. And they look like a vampire teeth, I call them. They just look like this. But in this case, we have the absence of those 3300 peaks tells me that nitrogen does not have any hydrogens connected to it. So that's a really important thing to understand from here. Now the other peak that we can see is here around 1680 or something. I cannot tell the number here, but it's really close to 1700, indicating the presence of a carbonyl carbon. So that's a carbonyl carbon, and there is nothing else. As you guys remember, anything after 1500 is nothing, and those are just CH stretches. So there's nothing that can help me from here. So now let's look in here. All right, so first thing first, we notice that we have that 2H peaks right here. And as I mentioned, there is a benzene ring. This confirmation indicates that my benzene ring is para-substituted. So that's one of the information that we have got. And we also know that there is carbonyl. And the other thing is we have a nitrogen that's connected to all carbons all around. Now, the first thing first is that we notice that there's this 1H peak at around 9.7 ppm. That tells me that this is a aldehyde. And because it's a 1H, that tells me that it's adjacent to a carbon with no hydrogen. So it's, if I want to like assume something, I would assume that's connected to the benzene ring. Right. Also, it's a little bit more downfield than it should be. It should be around like 8 and 9.5. But because it's a little bit more downfield, it could be due to that stability from the benzene ring. As you remember, conjugation increases stability, so it will shift it to the left. Now, let's look into that 4H right here. Also, we notice something here that there's not enough hydrogen. So 4 plus 4 is 8. 8 plus 1 is 9. And then there's 6, so that's 15 hydrogen. Oh, actually, never mind. That's exactly the number that we have. But there is something a little bit different due to symmetry that I will go over in a little bit. So if it's a 3 peaks, right? It has 3 peaks. and it's adjacent to a 4H. That doesn't, like, we cannot have a carbon that's connected to a 4 hydrogen. So that tells me that there's a CH2 and a CH2. Those are two similar CH2s that show only one peak on the H NMR. Right? Same thing with that 6H. We cannot have just one carbon that's connected to 6 hydrogens. So that tells me that there are two CH3s separately. And from that peak, we can see that there are 3 peaks. So 3 minus 1 is CH2. So I know that this CH3 is connected to a CH2. And that CH2 is connected to a CH3. And that 4H has 1, 2, 3, 4 peaks, indicating that this CH2 is connected to a CH3. Because 3 plus 1 is 4. So, now let's put the whole thing together. I know that my nitrogen is not connected to any hydrogen, and it has to be connected to those two. So the only other way it can not be connected to a hydrogen if it's connected to the benzene ring too. So if I were to assume a structure, I'll put the benzene ring from one side is going to be connected to an aldehyde, and from the other side I'm going to be connecting it to a nitrogen, which is connected to a CH2 CH3 and a CH2 CH3. So that 6H represent both of these hydrogens right here, and that 4H, let me change the color here, that 4H, let me use red, that 4H represent those two hydrogens, right, because they're similar, so they don't represent different peaks. And then that 1H represents the aldehyde due to its shift to the left, represent this hydrogen, and then those two hydrogens that are para-substituted are from these two right here. So I hope that made sense. Now let's move on into the multiple choice section. I'm going to have 5 questions going over some of the major chapters of Orgo 2, most likely. So for the last couple of questions from the ACS booklet, so first question is going to be asking us to consider the hydrogen atoms attached to the 3 different carbons, atoms labeled 1, 2, and 3, rank the attached hydrogen atom in order of most acidic to least acidic. And we talked about the acidity in previous lectures before, in Orgo 1 especially, and you guys have to remember that the more stable the compound is, the more acidic it is, and the same rule applies here, right? And stability is determined, in this case, going to be mostly determined by resonance stability. So let's start by comparing the first one. So what I usually do when I have such a question is I start by deprotonating the hydrogens. So CH3, let's start with the first one. Let's put it as a CH2 minus. So CH2 minus, connect to a C double bond O, CH2, C double bond O, O, CH2, CH3. So this one can resonate, kick off the electrons. Then you're going to end up with a CH2 double bond, CO minus, CH2, C double bond O, O, CH2, CH3. So remember, if it's a negative charge, having an electron withdrawing group is good. When it's a negative charge and there's an electron donating group, that's not good. So let's look at the second hydrogen. Again, so CH3, I'm going to start by deprotonating it. So C double bond O, CH, C double bond O, O, CH2, CH3. So if you can pick that from the beginning, this one will have 2 resonance structures. One from this side, picking up the electrons all the way to the oxygen. And then you have CH3, CO minus with a double bond, CH, and then C double bond O, O, CH2, CH3. Right, now let's look into the other side, right? So you can go either to the left or to the right. So this one has 2 resonance structure, indicating that it's even more stable than the first one. So it's going to be CH3, C double bond O, CH double bond, C O minus, CH2, CH3. So out of these two, we know that the second one is more stable because it has more resonance structure. Now look at the last one. Let me just move this a little bit down. So now let's look at the last one, which is, I know some of you are already able to tell that this one is going to be the least stable because of the electron donating group on it. Because remember, electron donating group does not stabilize the negative charge. So OCH minus CH3. And as you can see, this one does not even have one single resonance structure, right? It's not resonance stabilized. So, based on that, she asked us to rank the attached hydrogen atoms in order from most acidic to the least acidic. As I mentioned, this will be my most acidic, so being number 2. And then the second most acidic is going to be my hydrogen number 1. So 2, 1, 3. So between these two, I have to pick out D. So moving to the next question. Which compound is the product of an aldol condensation? So there is a trick here that you can do immediately to be able to figure out which one is going to be, but let's just try to break it down and see which one is going to be the product, right? So as I mentioned before, aldol condensation has to be an alpha beta, right? So looking at the first one, this is going to be the alpha carbon, and this is the beta carbon. So you can see if you break it right here, maybe this one will be correct. Let's move on though and see if there's something else. So this one's my alpha carbon, this is my beta carbon. So this one's probably not the answer. What about this one? This one is alpha carbon. You cannot break it right here. What about this one? It's alpha beta. This one is also not attached between the alpha beta. As you can see, this double bond comes from the OH. So let's look at the first one and try to break it down. Right? If I want to go backwards, that's what I'm trying to do. So it will be a CH3, C double bond OH. And that carbon should have a hydrogen here, right? 1, 2, 3, 4. Oh, no, it doesn't. So, yeah, this carbon will have a CH2 right here. And then the other structure would be a CH3, CH2, and then a C double bond OH. So what's going to happen is, remember, once we put it with base, this alpha hydrogen is going to get deprotonated. And it's going to attack this carbonyl carbon. It's going to go up. And then what's going to happen is you're going to have a CH3, CH2, CO minus, which will then get protonated to an OH. And then that will be connected to a CH, which is connected from one side to a CH3, and then C double bond OH. And then the dehydration reaction would occur, and that would look CH3, CH2, CH, with a double bond C, which is then connected to a C double bond OH, and then it's connected to a CH3 from here. So, luckily, it seems that the first one is going to be the answer. And there's a quicker way to be able to deal with this in this type of question, is that the double bond has to be formed between the alpha and the beta carbon. The reason to why is because of the dehydration. The reason why it occurs between the alpha and the beta, because it's going to form the most stable double bond because of the conjugation between the double bond O and the double bond right here, right? So you have a double bond, double bond, single bond, double bond. That conjugation stabilizes that double bond. That's why it's more favored than alpha. It's more favored than beta gamma double bond, right? So, and that's why you're not gonna see a bond that's forming between the beta and the gamma carbon. You're gonna see that double bond being formed between the alpha and the beta carbon, right? So, let me just look at the other ones for a second here. As you can see, this functional group, if that OH was here, then yes, maybe that would be a option out of these four options. So, because that OH is not on the beta carbon, that means that it's not an aldol condensation, right? And for this one is, as you can see, is the alpha. It's the alpha carbon. And remember, the alpha carbon is the one that's gonna form a carbon anion, and then will attack the carbonyl carbon. Now the last one, again, it's not it because the double bond is not being formed between the alpha and the beta carbon. So that's the fastest way to do it, right? And also another thing I should mention about double bonds is that I was talking to Dr. B, and she told me that you guys should focus when you're doing the exam. Make sure to focus on trying to solve the exam by hand, like you see all those steps that I did here, and not just jump into the answer, because sometimes it can be confusing. Like even though you understand it's the alpha beta bond, sometimes she's gonna put it in a way where she tried to it tricks you on the question, or so try to draw it out and then try to solve it as you're solving a free response question and not like as a multiple choice question, right? Just a quick tip. So, moving on to question 30, or question 3 in this case. So it's asking which of these reactions would be used to prepare this beta keto ester. So usually to form a beta keto ester product, you always want to have two esters that react together. It's also known as Claisen condensation. So what happens here is, it's also, again, it's the same thing. It's an alpha beta connection. All right. So what I do in this type of question is I solve every single one of these, and then I go back to see if it matches my result. So again, the first step is going to be putting the the reactant in a base. It's going to deprotonate the alpha hydrogen. In this case, the only alpha hydrogen I have is this one. So it's going to be a CH2 minus, going to a C double bond O, OCH3, which this negative charge then attacks the carbonyl carbon. It's going to go up, come back down, and kick off the OCH3. I just did it in one. It's not a one-step process. I just did it in one step just to be a little bit faster. So I have the benzene ring here. I have the C double bond O, which is then connected to a CH2, which is then connected to a CH2, C double bond O, OCH3, OCH3. Right. Now, because we're still in the first step, there's still base. So what's going to happen is the base is going to come back and grab that acidic hydrogen. And then what's going to happen is you're going to still form a carbon anion here. C double bond O, OCH3. And now, the second step of the reaction is an SN2 reaction. So we have a primary halide, which will be attacked using the carbon anion, CH2Br. It's going to attack this carbon, and the bromine, which is a good leaving group, is going to leave. C double bond O, CH, which is then connected to a CH2, CH3. And then from this side will be a C double bond O, OCH3. So that's the first one, which, based on this result, based on this answer, that matches our product that we want. So that's a good way of producing it. Now let's look at the second one. Again, we have a benzene with an ester, OCH3. And then we're attacking it to another ester. So plus CH3, CH2, CH2, how many carbons? 1, 2, 3, 4. C double bond O, OCH3. Again, the first step is going to be deprotonating the alpha hydrogen because this structure doesn't have an alpha hydrogen. So the only alpha hydrogen that we have is going to be this one. So I'm just going to deprotonate it, and then we have a negative charge right here. That negative charge is then going to attack the carbonyl carbon. It's going to go up, come back down, pick up the OCH3 group. And then my product is going to be the benzene ring, which is connected to a carbonyl carbon, or a carbon with a ketone, which is then connected to a CH, C double bond O, OCH3 from one side. And that CH is also going to be connected to a CH2, CH3 from the other side. But remember, guys, this is still in basic conditions. So what's going to happen to that CH is going to get deprotonated again and form a C negatively charged. And then the second step in the reaction is going to be just protonating it in water and H+. So then my product is as expected. So this is also a COCH3. Then you have a CH2, CH3. So this is also a good way to produce our product. And the last one, which is a little bit different than the other ones because this time we have an alpha hydrogen on the benzene ring. But this time is that we don't have two esters. We have ketone and we have kind of an ester. So for this one, it's a little bit different than the reaction that we used to see. So we have a benzene ring. So CH2, CH2, CH3, I think. 1, 2, 3, yeah. Plus C double bond O, OCH3, and OCH3. So for this one, what's going to happen is, again, the alpha hydrogen is going to get deprotonated. The only alpha hydrogen that we have in this case is going to be this hydrogen right here. So I'm going to go ahead and deprotonate it immediately, form a negative charge, and that will attack the carbonyl carbon, which is going to go up, come back down, and kick off one of those OCH3 groups. It's not going to kick both because it was only attacked once. If then it was attacked another time, then yes, it will kick the other OCH3 group. So I'm going to have the benzene ring, which is a double bond O, CH, CH2, CH3, which is then also connected to a C double bond O, OCH3. Because we are still in basic conditions, again, this CH is still going to be deprotonated, so it's going to be a C negatively charged, and that negative charge is really stable due to resonance. And then the last step is going to be protonating that, so it's going to be the benzene ring, connected to double bond O, CH, CH2, CH3, C double bond O, OCH3. Alright, so this one also works. Yeah, so the last one also works, indicating that both 1, 2, and 3 are good answers for good reactions to be able to produce that beta keto ester product. So my answer would be A. Alright, so moving on to the next question and the last one. So it's asking us, what is the expected product of this reaction? Oh, this is a good one. So, so for this one, again, you're bringing in a base, so what you have to do is you're going to deprotonate the alpha hydrogen. But see, in this case, it's a little bit hard to determine which one, right? So you have this alpha hydrogen and this alpha hydrogen. They're both, in this case, they both have alpha hydrogen. But how you're going to determine which one is going to get deprotonated is going to be the more stable one. And in this case, it's going to be the CH2, because it's resonance stabilized based on 2 resonance structures as compared to 1 resonance structure. So let's start by deprotonating. So it's going to be a CH connected to a C double bond O, OCH3, which is then C double bond O, OCH3, with the lone pair and the negative charge. And then we have this aldehyde, which is going to act as our electrophile. This carbon anion is going to attack the carbonyl carbon, and then it's going to form a CH3 CO minus, which is then connected to a CH C double bond O, OCH3, and then C double bond O, OCH3. And then, so in this case, a dehydration reaction will follow it. So what's going to happen is the dehydration reaction will occur, and there will be a double bond formed between the alpha and the beta carbon. And this is the alpha, and that's my beta carbon. So my product would look something like this. So CH3, C. Wait, I forgot. No, I'm fine. So C double bond C, which is then connected to C, which is then connected to a C double bond O, OCH3. C double bond O, OCH3. And then there's the H that I forgot right here. So that would be my product, and that based on that answer, C would be my answer. So that's pretty much it, guys, for this semester. I hope you guys all do well in the final, and good luck.